Hello Science 30s, welcome to physics. In physics we are going to be spending most of May in physics and we'll be learning a few things. First thing we'll be learning is about fields. And I want to define a field. A field is a region around an object in which another object will experience a force. So that could be a push or a pull. So we will be looking at three different fields in Science 30. We'll be learning about gravitational fields, we'll be learning about electric fields, and also magnetic fields. The first field that we're going to learn about is the gravitational field. So gravity is pretty easy to understand in a way, harder from a physical point of view to understand, but maybe we all understand how it works. We know that the Earth pulls us down towards it. And so a gravitational field is going to be an attractive force between objects with mass. Every object with mass then is going to have a gravitational field. So does that mean that a pen has a gravitational field? Yes, it does. Does the Earth have a gravitational field? Yes, it does. Now, obviously, the Earth is much bigger than the pen, and so that's why we would feel the Earth's gravitational field, but not necessarily the field that emanates from a pen. So this gets into what properties are actually important for gravitational fields. And so we've talked about one. We've talked about mass. So the mass of the object is very important. And also the other thing that's really important that we may not think about is going to be the radius, or how far from the object emanating the gravitational field is the test object. Okay, and so those two things are going to be really important. Before we get into the equations of gravity, I also wanted to look at what is the direction of gravity. So if here's the Earth right here, my question is, what direction is gravity? So no matter where you are on Earth, it's essentially always in the same direction. And the direction of that is going to be right towards this point right here, right at the center of the Earth. And so no matter where you are on Earth, here would be towards the center of that Earth, here towards the center, here towards the center, here towards the center, towards the center. You get the idea. And so it's always going to be, there should be really kind of infinite number of these lines, but I'm going to stick with just this many. Now, the other interesting part about drawing this in a way is that out here you see these lines are very far apart, whereas here they're getting closer together. And that's really nice because that actually tells us in physics that this is a very strong, it's stronger the field is stronger the closer those lines come together. And so basically out here, you're not going to feel as much of a gravity field as if you're closer to the center of the Earth. So we'll get into a couple examples here now of some equations. So the first thing we'll do is introduce the equations, and then we'll get into a couple examples actually. The two equations you can find are on page 2 of your data booklet. And there are the first two equations that are listed there under gravitational and electric fields. So right here and right here, those are the two formulas we're looking at. The first one is one that you probably might recognize. You definitely learned this in Science 10. This formula comes from F equals ma. And instead of F equals ma, because a in this case is acceleration, but in this case we're always going to be using g, we're just going to change that a to a g. And so then the formula turns out to be F of g, force of gravity, is equal to mass times the gravitational field strength. The second formula that we're going to be learning is little g is equal to big G little m divided by r squared. And so let's just go through now each of these variables. F of g. Nice thing about Science 30, guys, it's always right here. So it's always given to you, and very importantly, all the units are given to you as well, which is really nice in Science 30 to have those units given to you so you don't have to memorize those. So the first one is force due to gravity in newtons, and that's going to equal mass, which is in kilograms, multiplied by little g, which is going to be the magnitude of the gravitational field strength, and that is going to be in newtons per kilogram. Now you may remember that I said that G is the same thing as A. Well, you remember from Science 10, though, A is actually going to be in meters per second squared. And that is shown down here, though. What you have you don't even have to memorize this, because again, in Science 30, it's given to you, a Newton per kilogram is equal to a meter per second squared. And so you can use those two interchangeably in this course. Now, the second formula is the little g again. So you can see there is some commonalities between these formulas. Little g is equal to the gravitational field strength in newtons per kilogram or in meters per second squared. And that's going to equal big G, which is 6.67 times 10 to the negative 11 meters squared per kilogram squared. And that is a constant. That's just always going to be given to you because you always have it right here. You're always going to use this whenever you're using this formula. And then we see something else that's common between the last formula, which is the m, the mass, which has to be in kilograms. And then finally we get into our denominator, which is our radius squared. And that's in meters. So again, it's important to realize that it has to be in meters. And there we are. There's all of our two formulas and the breakdown of all the variables. Now for this next section, you're going to want to also have a calculator in front of you. So please, if you do not have a calculator, get a scientific calculator in front of you for this next little bit. So what we're doing is two example problems. These are from your textbook, and I'm going to go over them with you right now. So the first question is, the Earth's radius has an average value of 6.37 times 10 to the 6 meters, while the Earth's mass has a value of 5.98 times 10 to the 24 kilograms. Now, I always like to take a look at my units before I even start the question, and I see that I'm in meters for my radius, and I'm in kilograms for mass, which is, if we remember from back in our formula sheet, exactly what we need. We need to be in kilograms for mass and meters for radius. So that is a good sign. We don't have to do any work on that. So let's get to it. We need to first of all do what we always do with these types of questions, and that's define our variables. And so for A, R is going to equal 6.37 times 10 to the 6 meters. We have the mass, which is going to equal 5.98 times 10 to the 24 kilograms. And we have, and we're trying to figure out, by the way, the gravitational field strength. Well, if we go back to our formula sheet, we will realize the gravitational field strength is little g. So since we have R and M, we will then have to also use big G. And big G is going to be that constant that we learned about, which is 6.67 times 10 to the negative 11. And that's going to be in newtons multiplied by meters squared per kilogram squared. And there we are. And so now we're ready. We don't have to rearrange this formula or anything for this question. Little g is going to equal to big GM over r squared. And so that's going to equal 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And we're going to be multiplying that by the mass, which is 5.98 times 10 to the 24 kilograms. And then we're going to be dividing that by, the radius squared, which is 6.37 times 10 to the 6 meters. But then we need to square that entire thing. Do not forget to square the denominator. Very, very common mistake. So if you enter this into your calculator properly, you should come up with the answer of 9.829 ... And let's take a look at our units here. The kilograms here will cross out with one of the kilograms there, and the meters squared here will cross out with the meters squared here. and we are left with newtons per kilogram, which, as I've also said, or which I've already said, is also meters per second squared. For A, we can give a final answer, and that's going to be 9.83 newtons per kilogram. So I'm going to round that off to 3 significant digits. And there's my final answer for A. Now for B, B is a little bit different. We have to use that number and then continue our calculation. So for B now, a person with a heavy backpack has a mass of 100 kilograms and can be considered a test body for the gravitational field. Use the value from part A to predict the force of gravity Earth would exert on this person. So for B, we have a couple of things. We have G now in this case, which we've already calculated. Now, because this was a rounded number, I'm not going to use that rounded number in my next question. I'm going to use that whole number. And so this is going to be newtons per kilogram. So you would save that number in your calculator in some way. Okay, so use the memory or the last answer button, or if you have a TI-84, you can scroll up and pick that number, but do not use the rounded number if you're ever using that number in future calculations. We now need, because we're figuring out the mass of the test object is given to us, so we want to be using that now instead of the mass of the Earth. So for this formula for force, then we want to figure out the force due to the person's mass with that backpack. And then so here we are. So F of G, which is going to equal mg, which is going to equal 9.829 newtons per kilogram. And we're going to multiply that by 100 kilograms. Kilograms cancel out, and we're left with 983 newtons. And there we are. That is how we would do our first example problem. The next question that we're going to look at has to do with the moon now instead of the Earth. So they give us the average radius of the moon there, and they give us the mass of the moon there. Now right away, alarm bells are going off in my head because I see kilometers. Well, that's not good. We cannot be in kilometers when we do these calculations. And so what we're going to have to do first of all is convert those kilometers into meters. And so let's do that right off the bat. So we have the radius, which is equal to 1.74 times 10 to the 3 kilometers. And we know, you should know, that 1 kilometer is equal to 1,000 meters. And so what we're going to do is we're going to multiply this by 1,000 meters and 1 kilometer. And so what that will do is cross out the kilometers, and we land up with the number of meters, which is 1.74 times 10 to the 6 meters. So now we can jump in and start doing our questions. So for A, we have our radius, which is equal to 1.74 times 10 to the 6 meters. By the way, I didn't even say what we're calculating here in A. We're calculating the gravitational field strength once again, but this time for the moon, not for the Earth. The mass of the moon is given to us in this question, and it is equal to 7.35 times 10 to the 22 kilograms. That's nice that it's in kilograms for us. We already know big G. Big G is our constant, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And then we have our little g. That's all we need to solve for now. So we'll go over here and give myself some space to do this. Little g is going to equal big G m over r squared, which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. We're going to be multiplying that by the mass, 7.35 times 10 to the 22 kilograms, and then dividing this by r squared, which is 1.74 times 10 to the 6 meters, and that will be squared. Do this in your calculators and you will find out that the answer is 1.62 newtons per kilogram. And of course, that is the rounded answer. I'm just going to do the answer for B verbally, explain why the moon has different value for gravitational field strength than the Earth does. So it's because it has different values. I mean, it has a different value for the radius. The moon is much smaller than the Earth. And it also has a different mass because of that. And so it has a different radius and a different mass. While big G is the same, these other two values are quite different. And so that while we were at 9.81 or 9.83 for the Earth, we are only at 1.62 newtons per kilogram on the moon. So that leads us into the last question for this video, which is C. An astronaut in a new lightweight spacesuit has a mass of 100 kilograms and could be considered a test body for the gravitational field of the moon. Determine the force of gravity exerted on the astronaut by the moon's gravitational field. So for C here then, what we're going to be doing is defining our variables. First of all, little g is going to equal, and this was where we're going to be using the unrounded value again. So that's going to be equal to that. And we have our mass of the test object, which is this astronaut in this case, is going to be 100 kilograms. And we have our force due to gravity. Force due to gravity is going to equal mg, which is going to equal 100 kilograms multiplied by 1.619 ... newtons per kilogram. Let's forget that k there for some reason. Kilograms cancel out, and we are left with 162 newtons. So while the person on the Earth would have felt had a weight of 983 newtons, on the moon is only 162 newtons, and that's why when people walk on the moon, it looks like they are taking a leap. It's about an eighth of the value of the force of gravity.